Start this recording. Great. Move over here. So everyone got a copy of the practice test? The review day isn't for another week or so. I can't remember when it is. Oh, here you go. Is that the review day? Okay. So same deal. You're gonna do the practice test, but instead of me walking around and checking all your work, what you're gonna do instead is you're going to scan it somehow. You can just get a scanner app on your phone. Unless you already have one, then just use it. And just upload it on Moodle. So I put a little hand-in thing where you can submit it, and then I can go back and make sure that you got it in on time. Right? It has to be done before the review class, because then we go through it, and then of course you could just hand that in. So so make sure you grab. Did you get one? Who's new? Yeah. Did you get one? No. It's on Moodle. Yeah. So so that's what I mean. So a little bit different. So you're not going to show it to me. So you do have to do it in advance of the class, right? Upload it, because it won't accept any submissions past 6:30 on the 6th. Okay? So you have to get it in. Okay? And then it'll just be worth 1 completion mark. Just like the other one. Okay? And again, I'm not marking it. I'm just making sure you tried it. Okay? And then we'll go through it together in the review class. Okay? Any questions about it? No? All good? You kind of know the drill now with the practice test, but a little bit different with uploading it on Moodle, but it should be okay. So let me change this to here. Submit work for practice test 2. On Moodle before 6:30 on March 6th. Thank you. All right, let's do a little bit of review. Not too much because there's a lot we have to go through today, but and it was just on Monday, so no big deal, right? But what did we do last day? We just talked about how do we solve for the future value? How do we solve for the present value? Right, so we talked about compound interest. And solving for the future value. And we solved for the present value. In the formula, the future value is PV times 1 plus I to the power of n. Just to refresh our memories, right, because we're going to use this a lot today, where I'm assuming you know future value and present value, right? If not, you can look at the notes from last day. But where I is the periodic interest rate. And the calculation is I equals R over F. R is the annual rate, so the nominal rate. R is the nominal rate. And F is the compounding frequency. So last day we went through and we made a table of all the compounding frequencies. Some main ones that we have to keep track of are, well, semi-annually, twice per year, right? Weekly, 52, bi-weekly, 26, daily, 365, right? So we made that table last day, right? And you have to know those frequencies. It's just how often are we compounding, right? So, and N is the number of compoundings. Number of compoundings. And N we calculate as time times frequency. For time, T is time in years, just like it was for simple interest. So T stays the same, R stays the same as before, but now we have to calculate N instead of T and I instead of R. Any questions about that from last day? All right. Let's start. 5.3 has a really long name. It's calculating the periodic interest rate interest rate, that's I, right? Lowercase I. Because remember, what was uppercase I? Uppercase I was the amount of interest in the simple interest scenario, right? So lowercase I is the periodic interest rate. And the number of compounding periods. And the number of compounding periods basically solving for N. Okay. So just like before, we're just going to keep going and solving for each of these components in our formula, right? Slice it and dice it so that we're comfortable solving for anything in this equation. So we'll start with solving for I. We'll start with the general equation, just kind of rearranging it for I, see what it looks like. But if you have a look at your formula sheet, right, all these formulas are derived for you, right? So on the test, you wouldn't have to show me how you got to that formula because it's on the formula sheet, right? So here, I'm just showing you so that you know where it came from, but it's not important for you to know. It's more applying these things. Okay? So we start with the future value is the present value times 1 plus I to the power of N. We're trying to get I on its own, right, which means we're going to divide both sides by PV. So we get the future value over PV is 1 plus I to the power of N. We need to get rid of that power of N, which we've talked about, but it was a long time ago, right? We're going to take the nth root of both sides. And so we take the nth root, which we denote by, fine, putting a little n in the hook of the root, right? So we're taking the nth root of the future, the future value over the present value. By taking the nth root of something to the power of n, I'm not even going to bother writing it out. It's just 1 plus I. And I don't need those brackets. I just keep them on there for a little bit longer. Now, to get I on its own, all I have to do is subtract 1 from both sides. So then I get, and my little switcheroo, I like to put what I'm solving for on the left-hand side. So I just kind of revolving door switch it. So I is the nth root of the future, I keep writing p, but future value over the present value, all minus 1. Which, surprise, surprise, is exactly what's on your formula sheet. Right? So that's where it came from. So I'll just highlight it, show you it's on your formula sheet. Any questions about deriving that? Let's have a look at an example then. Example 178, let's do. So again, this is a really kind of simple problem, but I'm still going to do a timeline, even though I don't really need one. Oh, here. I'm still going to do a timeline just to get in the habit of making these timelines. Okay? Because we've got 15,000 was invested for 13 years until it reached a value of 30,000. Right? So we have the present value, we have the future value, we have the amount of time that it sat there for. If interest is compounded monthly, what was the nominal rate of interest? Okay. So we want to find R, right? But we've got this compounding going on. So first we have to find I, and then we can find R. So for compound interest, we have this extra step both ways, right? When we're solving problems where we need I, we have to solve for I, but also we're always going to want to find R and not just I. Okay. So let's just highlight. Oh, Duchamp. Trying to catch everyone. But if you didn't get a practice test, you can grab one after. Trying. Stop. So just going through here, you see, yeah. I'm just gonna jot down what every little thing is before I make my timeline, right? You could just start with the timeline, but sometimes it's nice to kind of break it down. 13 years, that's T. And then the future value is 30,000. If interest is compounded monthly, what that's saying is that F must be 12, right? Our compounding frequency is monthly, so 12. And what was the nominal rate? That's R. Right. Keeping that in mind. So in terms of a timeline then, like I said, really kind of simple, but let's do it anyways. It doesn't say when you deposited it and when you are taking it out. But so for simplicity, I just say, here's today, and here's 13 years, right? It doesn't matter. You could make today and 13 years ago. As long as the distance is 13 years, you're fine. Okay. So always put the dates on top, the amounts below the tick marks, right? So here today you deposited 15,000 and then it grew to 30,000. For compound interest, we don't just put the time on the arrow, we put n, the number of compoundings. So n is time times the frequency. That's on your formula sheet. Time in years is 13 times the frequency, which is 12, which is 156. Guess I should grab my calculator just in case. I've got it here, so that's why I'm confident, but for later. And then we want to find I. So we can use the formula that's on your formula sheet. I is the nth root of the future value over the present value, all minus 1. You don't want to forget that minus 1 because it's going to make a huge difference. Right, you'll see in a little sec. So we'll start by plugging in the values and then see what we have to do. Oops. So we want to take the 156th root. Oops. It's a little tricky to draw, or at least for me, maybe. Haha, I did it. Should have done the root first and then put the 156 in. Oh well. The future value is 30,000. And the present value is 15,000. All minus 1. We can simplify this because 30,000 divided by 15,000 is just 2, right? So we've got the 156th root of 2 minus 1. Hard to do on your calculator, right? But if you remember, if you have to take any root that's not the square root's the only one that's built into your calculator, right? What you do is here, we have to take 2 to the power of 1 over 156. Right? And that's how you're going to do it on your calculator. So what we do is we have 2, I'll put brackets around it, to the power of 1 divided by 156, and then minus 1. So try it on your calculator. 2 to the power of, and whenever you want to do a power that's not, I guess, just 2, use the y to the x button. And then I'm going to put the 1 over 156 in brackets just to make sure that it stays together. So 1 divided by 156. So for the 2 to the power of 1 over 156, I get 1.004453137, then minus 1. So you'll want to make sure that you get the same answer. I'll show to the side here on calculator, just because maybe we're not all familiar with it. You're going to hit the 2 button and then the y to the x button. And then I throw in the bracket button. 1 divided by, I'm cheating and doing 156 as one button. I think we all get it. Round bracket, and then equals. Some of my buttons are bigger than others. This is a 1. Okay. Hopefully everyone was able to get the 1.0044 whatever. So now we have to subtract 1. So our I, right, which is the one we're solving for, is actually 0.004453137. And just for later, because I know I have to use this value, I'm just going to make a note that I'm storing this in 1. It's really important that we subtract the 1, right? Because otherwise, right, if you think of these as rates, right, I is the interest rate. If you just have this value, 1.004, that means that every month you have a rate of 100.445%. That would be really good, but also it won't happen, right? And so this is more reasonable for you to get every month because it's the periodic interest rate. So that's why it's going to make a huge difference in your calculations if you're making 0.4% or 100.4%, right? So you have to subtract that 1. Okay. We always need to solve, didn't come out right. We always need to solve for the nominal rate, R. And so we always need to solve for the nominal rate, which is R, right? Here we found I. So remember, I is R over F. You can use I, you know I, and you also know F. F is the compounding frequency, which is 12 for this question. Okay. And so we know I was 0.00445337, which is R over F, which is 12. So whether you stored it in your calculator or you just have it on the screen still, times it, we have to multiply both sides by 12 to solve for R. So R times 12 is 0.053437644. Or R is 5.34%. If you do that little check-in where you convert it to a percentage, you should be able to tell pretty quickly if it's a reasonable value or not, right? Usually these rates are not higher than 10% even, right? So usually they're kind of in the realm, kind of less than 10%. Right? It's possible that it's higher, but usually not. Okay? So for these questions, right, you're first going to find I, and then you can find R. Any questions about that? Okay. All right. Solve for N. So do it all over again. Slightly different. Solving for N. Again, I'm going to start with a general formula, show you how we got to the formula on your formula sheet. But in terms of using it, you just have to be able to use the formula. So we start with the future value is the present value times 1 plus I to the power of N. for solving for n, we have to divide both sides by PV, right? Trying to get n on its own. So we do future value over present value is 1 plus I to the power of n. The trick, and why we had to learn about logs, the trick to bringing that n in the power down is we have to take the log of both sides, right? So we take the natural log of both sides, and by the log laws, we can bring that power downstairs. But that means we have to take the log of the future value over the present value, which is the log of 1 plus I to the power of n. But by these laws, we can rewrite this as n times the log of 1 plus I. Just because of how logs work. And then the log of the future value over the present value stays the same. Now we can solve for n by dividing both sides by the log of 1 plus I. But again, I'm going to do that revolving door where I put n on this side is the log of the future value over the present value divided by the log of 1 plus I. I say log, but it's really ln, right? The natural log. Okay. And again, no surprise, it's the exact same as what's on your formula sheet, right? So, and again, you don't have to know how to solve for it, although it's a pretty good bonus question. Make a star. Knowing how to solve for these trickier ones. Okay? But besides that, no, you don't need to know how to solve for it. Okay? So, any questions about solving for it though? Then let's do an example. Example 179, let's do. So for these problems, it's not going to ask you to solve for n, right? Just like it wasn't asking you to solve for the periodic interest rate, right? It was asking for the nominal rate, and to get there, we had to solve for I. Same idea here. Here, we're asking, okay, in order to save for college, you want to invest $10,000 and have it grow to $15,000. Fair enough. If the rate of interest is 8% compounded semi-annually, how long will it take for this to occur? Right? So we want to know what's t, so solve for t, right? But with compound interest problems, we can't just solve for t because there's no t in the formula. So we have to solve for n, and then we can solve for t. Right? So again, I'm just going to jot down what each of the items that have been given are. So we invest a present value of 10,000, and it's going to grow to a future value of 15,000. If the interest rate is 8%, so R is 0.08, compounded semi-annually, that's what tells us our frequency is 2. How long? We're solving for t. And again, even though it's like kind of a simple thing, you invest some money and it grows to some amount, I'm still going to do a timeline just to make sense of it all. So we've got here. Let's make this today. And then here, the whole question is asking how long is it going to take, right? And so I'm just going to put a question mark there, right, to show that I don't know how long it's going to take. That's what I'm going to find. So today I put in 10,000, and I know I'm going to let it sit there until it's grown to 15,000. I is R over F, which is 0.08 divided by 2. So our periodic interest rate is 0.04. And N, we don't know. Need to solve for N before we can solve for T. All right. We'll just use the formula on your formula sheet. So we've got N is the log of the future value divided by the present value divided by the log of 1 plus I. So we already determined what each of these were. So we're going to have the log of 15,000 divided by 10,000 over the log of 1 plus 0.04. Once you simplify inside the log, it's not that bad, right? You have the log of 1.5 over the log of 1.04. I'll make a note here. For example, to solve for the log of 1.5, log of 1.5 on your calculator, how do you do it? On these calculators, right, you have to have the 1.5 on the screen. Pretty sure, let me check. Yeah, 1.5 on the screen. And then hit the LN button, which is over on the left-hand side. Kind of 1, 2, 3, 4, fourth button from the bottom. Sixth button from the top. So then hit the LN button. I think that's all you have to do. And then equals, just in case. Turns out you don't have to, but sometimes it doesn't show you the answer until you hit equals. So it's good to get in the habit of just always pressing equals after. And I get, which is 0.405465108. So make sure that that's what you get when you try your calculator doing the log of 1.5. So this becomes 0.405465108 divided by, and I'm going to store this in 1, just jotting that down. And then 1.04, take the log of it, is 0.0392200713, and I'm going to store that in 2. So now if I take the first one divided by the second one, recall 1 divided by recall 2, you should get an answer of 10.3 10.33803,507. So make sure that's the answer that you get. You don't have to show this middle step here, definitely not. Right, so you don't have to show this. You can just go straight from this to this, that's fine. I'm just showing it to you so you can check your calculations, your calculator work. So N is 10.33803507. Here's the thing. We can't tell the bank to stop after 10.33803507 compoundings, right? They would say, no thanks. We're just gonna go to either 10 or 11. What's it gonna be, right? And so 10 compoundings, we wouldn't quite be at the 15,000, right? Because you're earning interest and you're letting this grow to 15,000. So at 10 compoundings, you haven't quite reached your goal, right? So you have to go to 11 compoundings, right? So when you're solving for N, you're gonna get some value like this, but then you have to remember that, okay, I have to go to 11 compoundings, right? So we have to round it to the next whole number, right? So not the nearest whole number, the next whole number. So since we can't since we can't have 0.33803,507 of a compounding, we will need to round up to the next whole number whenever we're solving for N. Whenever we are solving for N. So we would need N equal to 11 compoundings. When we talk about time, how long is it going to take? So your friend asks you, oh, how long is that going to take? And you say, oh, just 11 compoundings. They would probably say what? So we have to convert this to time, right? And so we use that same formula. N is time times the frequency, but now we're solving for T instead, right? So now we can solve for T. N is time times the frequency. And we're forcing to be 11. T we want to solve for. And F, what was it? Semi-annually, so 2. Okay. So now T is 11 divided by 2. 5.5. T is always in years. And for T, we can have decimals, right? 5.5 years. We all understand what that is. In fact, you don't have to convert it to 5 years and 6 months or anything silly like that. We're just going to take T as a decimal. In a question, I would tell you to round T to 2 decimal places or something like that, okay? If it's necessary. Any questions about that? Okay. Okay. Here's a fun one. It's the doubling time. Who's heard of the rule of 72? No? I think you will, because sometimes people have and sometimes people haven't. But so doubling time, also known as the rule of 72, the rule of 72 is just a quick way to figure out how long is any investment going to take to double, right? So it's just a quick way to say, okay, if I know the rate, then it doesn't matter if I deposit $1 or $1 million, how long it's going to take for it to double is going to be the same, right? And so as long as we know the rate, we'll be able to figure out just a quick approximation of the doubling time. So, given a rate, the rule of 72 lets us find a quick approximation, find a quick approximation for the doubling time. And this works for everything, not just interest rates, right? It could be for population rates. It can be for, I don't know, disease rates. So any rate that you can think of, we can use the rule of 72 just to get a quick idea of how long is it going to take to double. So what it says is that the doubling time, which is in years, is roughly, remember this is just an approximation, so that's why I have the squiggly equals, right? Approximately equal to 72 divided by the percent annual rate. Notice that it's the percent rate, right? So 8%, you would just use 8, not 0.08. So this is the only time where we're not going to convert it to a decimal. We just keep the percentage. Okay? So this is going to be the same as 72 divided by R percent. I'll just make a note here. In finding the doubling time, we will use the percent annual interest rate, which means this is the only time, and can't remember if this is the course or the other course, but anyways, this is the only time where we're gonna use just the percentage, right? Otherwise, we always convert it to a decimal, right? So this is the only time we won't convert the rate to a decimal. So as a little example, let's do example 181. notice in this formula, if you're solving for the doubling time, you've got 72 divided by the rate. So the only thing that you need is the rate. Right? In this example, we're given the present value, right? The initial deposit. So an investment of 15,000 needs to double. So you could use that. You could say, okay, well, that means 15,000 has to grow to 30,000, right? But we don't actually need that information. Right? At a rate of 8% per year, roughly how long will it take? Right, so roughly how long is this going to take? So you could go through and calculate and find n, just like we did just earlier, and then solve for t, right? How long is this going to take? Or if you just want it to double, you can use the rule of 72, which says that the doubling time in years is roughly equal to 72 over r%, which in this case is going to be 72 divided by 8. Roughly 9 years. So that's a pretty good tool. For example, if you go to the bank and they offer you an interest rate and you want to know if you would be happy with that or if maybe you need a better interest rate, right? So the doubling time, you just take 72 divided by the rate that they just gave you. And for example, if it would take you 50 years to double your money, maybe you're happy with that, maybe you're not happy with that, but at least you have a gauge to say, okay, well, this is how long it would take me to double my money. Do I like that or not? Right? And so that's why I find this this quick little rule is really fun and just kind of useful. Right? Any questions about that one? So you could do things like, so any multiples of 2, right? How long would it take for my investment to quadruple? Times it by 4. Well, that's double it and then double it again, right? So it would take 18 years. Right? So any multiple of 2, any multiple of doubling, you can figure out. Okay. 5.4. So now we've gone through this formula sheet, right? We've solved problems for the future value. We've solved the present value. We've solved for I. We've solved for n. We went further and solved for r. N, we went further and solved for t, right? And that's how those questions are going to go. But now we'll get into kind of more applied questions. So 5.4 is on equivalent payments and payment streams. Which we've already seen once in the simple interest case, right? Now we're seeing it in the compound interest case, but the idea is the same. So we'll just start with an example. Example 185. What I want to do. So usually how these questions go, and this is why I steal the problems. So how these problems usually go is someone borrowed some money. they need to make arrangements because they can't pay it back, or they want to change their repayment plan to something else, right? And so we have to figure out what the equivalent payments are. So here we go. Doug's original intention was to settle a financial obligation with 2 payments. So he had a loan and he's gonna make 2 payments. The first payment of $1,500 was due 1 year ago from today. The second payment of $2,500 is due 3 years from now. Okay? Doug missed the first payment and now proposes 3 payments that will be economically equivalent to the 2 originally equivalent scheduled payments. I think there's too many equivalents in there, but whatever. The replacement payments are $1,000 today, and a second payment in 1.5 years, and a third payment twice as large as the second in 3 years. So we've already seen problems like this, right? Just not with compound interest. What should the second and third payments be if money can earn 8% compounded semi-annually? Okay. When we have these kind of big wordy questions, right, we definitely want to make a timeline, right, to map out everything that we have, what we need to solve for, how we're going to get there, right? And so you're going to want to put a lot of time into your timelines, and then your calculations will be easy, right? First thing you're going to want to do is just figure out what dates, how many dates do you have to put on this timeline, right? And so we've got the original payments and then the new payments that we're going to put on here. So let's do the old payments. So what I'm going to do, because it gets really messy if you try to put everything on one timeline, what I'm going to do is I'm going to do a timeline for the old payments and then a timeline for the new payments. But I'm going to have the ticks all the same for both the timelines. And I'll show you what I mean. So let's go through and read this again and just figure out how many dates we have to put on there. So we have a year ago from today. So we have to put today on there just as a reference point, right? So a year ago today, 3 years from now, and then he's going to make a payment today, so that's already on there. And then a second payment in 1.5 years, and a third payment in 3 years, which we actually already have a payment from the old payment schedule that we had to put on there. So we only have 4 dates that we have to put on this timeline. Okay. So what I'm going to do, I draw a line as big as I can afford on my page. And then I'm going to put these 4 ticks on here. And remember, you don't have to figure out where they would go, right? It's just, I just put them kind of equally spaced to get an idea of what's going on. So I know that this one has to be today because this is 1 year ago. And then my next one is at 1.5 years. And the final one is at 3 years from today. So it might be helpful to read through this blurb and just kind of jot down the dates that you have to deal with on the side, and then you can sort them after, right? I've seen this problem before, so I know, and I also have it here, right? But if you're doing it for the first time on your own, then maybe just jot them down, right? We've got today, we've got a year ago, 3 years, 1.5 years, and then you can sort them and put them on the timeline later. So, like I said, I'm going to have this same setup for both of my timelines. Right? And you can put them all on the same timeline. It just gets really messy. Right? So now we're going to put the dollar amounts down below. So the dollar amounts for the old payments was $1,500 a year ago, and a second payment of $2,500 is due 3 years from now. It's not quite clear from reading the question where we should draw these payments to and make them equivalent. And it really doesn't matter, because as long as you figure out what both of these payments are worth on one day, and then you make the other two payments worth the same on that same day, it doesn't matter what day you pick, right? As long as they're equivalent, it doesn't matter, right? And so here, it doesn't matter what you pick as the focal date. On a test, I would tell you, use this as the focal date. Right? So I'm going to say that here. Use, oh, you know what? Use 1.5 years as the focal date. You'll see why I picked that in just a second. So now what we're saying is that, okay, here's our focal date. So what that means is, all right, both of these payments, we have to figure out what they're worth 1.5 years from today. And so this 1,500 is going to get pulled forward to some future value, and I'll just denote it 1 because that's the first one I'm going to calculate. Right. So the subscript don't matter to keep track of. Then find also to 100, it's going to get discounted to a present value 2. These two added up is the total value of original payments. I'll just say original. I ran out of room. Maybe I should write original payments instead. There. Old sounds not as nice. Old payments, new payments. So that's the original payment schedule. Right? You're going to find out what it's worth at 1.5 years. And then what I'm going to do here, well, let's finish this timeline first. So here we've got on the arrows, we're going to put n. Right? N is time times the frequency. Time is the distance of the arrow, right? From 1 year ago to 1.5 years from now, time is 2.5, right? Time is 2.5. And the frequency, what should the second and third payments be if money can earn 8% compounded semi-annually? So the frequency is 2. So I've got 5 compoundings in there. Same idea here. N, I'm not going to write out the formula because I don't have that much room. But between 1.5 years and 3 years, there's 1.5 years. So I've got 1.5 times 2 which is 3 compoundings. So, and maybe as a little, just so I don't forget to do it, I is R over F, and R is 8%, so 0.08 divided by 2, 0.04. And it's the same for both of these payment plans. Okay? Perfectly reasonable for the rate to change. Right? The original payment plan had a rate of 8% compounded semi-annually. Now you revise the payment plan, but now the interest rate is 10% compounded quarterly. Right? So you have to keep track of those. In this case, the periodic interest rate is 0.04 for both of them. Right? But it could happen that you have different interest rates, so you have to keep track of that. So there's your original payment plan. Right? So now, here's our revised payment plan, or maybe new payment plan. Revised payments. So like I said, I'm going to keep the top all the same. 1 year today, 1.5 years, and 3 years. And again, 1.5 years has to be the focal date, right? You have to bring these to the same date for them to be equivalent. Focal date. So the new payments were a little bit different, right? Because we've got, so the replacement payments, that's what I should have called them, not revised, but replacement or whatever, are $1,000 today. I'll jot that down. $1,000 today. And then a second payment in 1.5 years. So we don't know what that is. So we've got this unknown payment situation. And a third payment twice as large as the second at 3 years. So remember we did this last day where we have, okay, well, X and then 2X at 3 years. Right? We don't know what X is, but we're going to solve for it. Regardless of what they are, right? They all have to be worth the same as the total value of the original payment plan 1.5 years from today. So we pull this guy forward to some future value. 3, it's my third calculation that I'm going to do, so I'd do 3. And then 2X becomes some present value 4. Don't forget about this X here, right? X is an amount that we're solving for, right? X plus future value 3 plus present value 4, those 3 are the total value of the revised payments. Total value of revised. In order to be equivalent, right, you wouldn't agree to this repayment plan unless it was equivalent. So in order to be equivalent, we know that the total value of original must be the same as the total value of the revised. which in terms of our calculations, right, the total value of the original is future value 1 plus present value 2. And that has to equal the total value of the revised. We're not going to forget about that x because that's an amount. X plus future value 3 plus present value 4. So we know how to solve for unknown payment amounts, right? Just not in the compound interest sense. I can't remember if we did it already. Anyways, probably not. But we know how to solve for unknown payment amounts. All we need to know is, okay, well, what do they have to equal, right? But we'll be able to solve for future value 1 and present value 2, so we'll know what they have to equal. Right? So here we go. We have to solve for each of these values. So we'll start with future value 1 is the present value times 1 plus I to the power of n. The present value of future value, oh, I forgot to put the n's on the arrows. That's, and for this little guy, from today to 1.5 years from today is just 1.5 times 2, which is 3. And again, from 1.5 years to 3 years is also 1.5 years. I'll cheat and just say 3. It's the same. All right, now we can keep going. For future value 1, the present value is 15,000, or 1,500, sorry. So we've got 1,500 times 1 plus I, which we calculated to be 0.04, to the power of n, which for this arrow in particular was 5. Right? For all the rest of them, it's 3, right? But you have to keep track of what your n is for each problem that you're doing. So to the power of 5. So we have to solve for inside the brackets, right? So 1.04 to the power of 5, and then multiply it by 1,500. So we get 1.04 to the power of 5 times 1,500. I get 1,824.979,354, which in money is 1824.98. Great. Moving on to present value 2. And again, we can use the formulas on the formula sheets because they're given to us. So the present value is the future value over 1 plus I to the power of n. For present value 2, the future value is 2,500. So we've got 2,500 over 1 plus 0.04 to the power of n, which we found was 3. So again, we have to simplify inside the brackets, so 1.04, and then to the power of 3, and then we can divide 2,500 by that. So we get 1.04 to the power of 3, and then 2,500 divided by that. I get 2,222.490897, which in money is 2,222.49. So now, if you wanted to, you could figure out what the total value of the original loan is, but I'm just going to leave it for now. I'm going to keep doing my calculations, right? Find future value 3, right? Because next stop, future value 3 and then present value 4. Future value 3 is the present value times 1 plus I to the power of n. You can see that once you've made your timeline, right, making the timeline is the hardest part, right? But once you have it, then you know what you have to solve for and when. Future value 3 has a present value of, I want to say 1,000. 1,000 times 1.04 to the power of 3. 1.04 to the power of 3 times 1,000. We got 1,124.864, which in money is 1,124.86. Now we can solve for present value 4, which is the future value over 1 plus I to the power of n, which is going to be, the future value of this one was 2x. Right? We don't know how much it is, but all we know is that it's 2 times the payment at 1.5 years. Right, so 2x divided by 1 plus 0.04 to the power of 3. 1.04 to the power of 3. And then what I'm going to do is I'm going to simplify this, right? I've got 2x divided by 1.124864. But I want to get something times x, right? So I want to do 2 divided by 1.124864, right? And then that's going to be by x, or times by x. So what I get is that this is actually 1.77799217x. Right. What I've done is I've separated the 2 and the x, right? And I've said, okay, hold the x to the side. Let me simplify this, and then I can multiply by x again. Right? So I kind of pulled them apart in my mind, simplified that to one number, and then I get the 1.77. Because I have to use this later and I have to use all the decimal places, I'm definitely going to store this. I don't think I've used any stored options before for this question, so I'll store it in 1. Okay. So, okay. So now we know, right, that the total original has to be the total, what did I call it, revised? We'll start there again. So we said future value 1 plus present value 2 has to equal x plus future value 3 plus present value 4. We have all these values now. So what we can say is that's the same as 1824.98 plus 2,222.49 has to equal x plus 1,124.86 plus I ran out of room. 1.7777992717x. Well, I'm going to move it down. I know. Plus 1.77. But if you had room, you're gravy. 992717x. I almost didn't give myself enough room again. Close. Okay. So what we have, right, is, well, on the left-hand side, we can just add those up and we have a number, right? So let's do that. I get 4,047.47. And on the right-hand side, I've got x plus just the number plus some other value of x, right? So I can combine like terms, and I can rewrite this as 1124.86 plus x plus 1.7x is 1x plus 1.7x, so that's 2.77 whatever x. So we get 2.777992.717x. So now I'm going to add 1 to my calculator here. Store that again. So solving for x now, I can subtract 1,124.86 from both sides, and I can get 4,047.47 minus 1124.86 is 2,922.61, which is 2.777992.717x. Okay. Just moving that 1124 over to the left-hand side by subtracting it. And now, solving for x, x is 2,922.61 divided by 2.777992.717, which is why I encourage you to store it. So x is 1,052.058194. So in money, x is 1,052.06. All right. We didn't just want the payment at 1.5 years. We also wanted the payment at 3 years. So now find 2x. 2x is just 2 times 1,052.06. $2104.12. So the new payments would be $1,000 today. It wasn't asking for that, but I'll figure I'll just throw it in there. It would be 1,052.06 in 1.5 years, and 2104.12 in 3 years. This payment plan, right, is equivalent to the other one, the old one, because we force them to be the same on the same date. Any questions about that one? Oh. So let's do another example. But it's the last one. How about that? I'm going to ignore the shaking of the head. Oh, you don't need to. I know, but I kind of do though. Or maybe the head shake was because you want more examples. I know, right? More examples. I feel like all we do is examples. Okay. I've decided to make annual contributions to a fund in order to have $10,000 in 3 years so that I can purchase a car. That sounds great. Each contribution will be of equal value, right? So we're going to have these equivalent payments. And the fund into which I'm contributing earns a rate of return of 4.4% compounded quarterly. Convenient. How much must I contribute each year? Okay. So we're making annual contributions, meaning I'm making contributions each year. Okay. And so to map this out for 3 years, I can start today, and then I've got a payment at 1 year, a payment at 2 years, and a payment at 3 years, and then I'm done, because then I should have $10,000 in the bank. So in terms of our timeline, right, we've got 4 ticks. So just jot down my 4 ticks. Starting today, and then a year, and then 2 years, and finally 3 years. So I'm going to assume that we're making a contribution today. It's not clear from the question, but I'm going to say that that's what we're doing. So X, remember these are equivalent payments, but we don't know how much they are. All we know is, well, they have to add up to $10,000 at 3 years. Right? And so we've got a payment here at 2 years and a payment at 3 years. So I like to draw these arrows, right, starting from the one closest to the focal date. Here, there's only one possible focal date. Right? Well, you can make your work a lot harder, right? But the most obvious focal date is at 3 years, because you know that all of these have to add up to $10,000 at 3 years. Right? Focal date. So even though it doesn't say, right, it has to be at 3 years, because that's where you know how much they have to be worth. So we're going to draw all the arrows to 3 years. So I start at the one closest to it, and I say, well, this is future value 1. This is future value 2. And this here is future value 3. And I'm going to force these to total $10,000. Why would I say that any other focal date would just make your life harder? You could say, okay, well, I want to use today as the focal date. Fine. But then you have to figure out what $10,000 is worth today as well. Right? So then you just have to do more calculations, which doesn't really make sense. You could do that, but why? On each of these arrows, we're going to put the number of compoundings, right? So we've got n between 2 years and 3 years is just 1 year. And what's our frequency? Compounded quarterly, so 4. 1 times 4 is 4. Moving on to the next one. Between 1 year and 3 years, right, that's 2 years, so you got to keep those straight. 2 times 4 is 8. And finally, n is between today and 3 years. You have 3 years times 4, which is 12 compoundings. The rate of return, so the interest rate for all of these is the same. And so we've got I. Oh, thank you. Nicola. Thank you. So I is R over F, right, from your formula sheet. R is 0.044, and we're conveniently compounding quarterly, so divide it by 4, so 0.011. All right. We've got all our pieces for our timeline. Right. Now we can just get to work and do these calculations, right? We'll start with future value 1. Future value 1 is the present value times 1 plus I to the power of n. The present value for all of these is going to be x. And so the only thing that's changing, I is the same. The only thing that's changing is the n for each of the arrows. Right? And so we've got x times 1 plus 0.011 to the power of 4 for this one. This is where you want to be careful with picking the right n for the one that you're solving for, but besides that, it's breezy straight. Okay. So I get 1.011 to the power of 4 times x. I get 1.044731339, oops, 9 x. I'll store this in 1. I'm going to need to use that value later on, right? So now I'm going to jot down that I stored it in 1. Moving on. Future value 2 is still the present value times 1 plus I to the power of n. Present value is still x times 1 plus I is still 0.011. N now is 8. 1.011 to the power of 8 is 1.0914637 times x. Before I forget, I'll store that in 2. And future value 3 is PV times 1 plus I to the power of n. PV is still x times 1 plus 0.011 to the power of 12. 1.011 to the power of 12. I get 1.140286196x, and I'm storing that in 3. Okay, so now we have all these future values in terms of x. Don't forget about that first x, right? The x at 3 years. It's also because you're going to make a payment at 3 years. right? So it's going to get added to all those future values to make 10,000, right? Really common mistake. So that's why I pointed out, right? If you've got an X at the focal date, don't forget to add it in. So we know X plus the future value 1 plus future value 2 plus future value 3 has to equal 10,000. Which if I flip these around, yeah. Oh. Future value 1, huh? Let's see.
Oh wait, no. I'm missing 0.
Oh. I was like, uh-oh, because that means I did it wrong twice. That is a relief, actually. So 10,000 has to equal X plus future value 1, which is 1.044731,339X plus 1.09146357X plus 1.140286196X. Luckily, I've stored all those, so I don't have to type them in. Remembering that little x, right? 1x plus 1.04x plus 1.09x, right, etc. So I have 1 plus recall 1 plus recall 2 plus recall 3. So we have 10,000 is 4.27648110.5x. Solving for x, where it's so close. X is 10,000 divided by 4.27648110.5. So I get X is 2,338.371141, which in money is 2,338.37. Right. So each payment today, a year from today, 2 years from today, and 3 years from today has to be $2,338.37 to total $10,000 in the end. Each payment must be $2,338.37. Any questions? No. So I guess on Monday, I'm going to show you how to solve these problems on your calculator. And they'll be way faster to do it on your calculator. Right, so we'll start using these white financial buttons, right? And you'll see why you have to have this calculator next day. Okay? Yeah, if there aren't any questions, make sure you get the practice test so you can get started on it. You can do, I feel like you can do all of these questions. Yeah, you can do all these questions. I guess have a good weekend. See you on Monday.